Chapter 10, Lesson 2 can be found on page 288 in your textbook. In today's lesson, we're going to begin by reviewing what we learned in Lesson 1, all about motion. Number 1, how is displacement and distance different? Remember in our definitions that displacement is distance, but it's also factoring in the direction in which you've traveled, where distance is the total amount of length that it's added together to find out where that motion is taking place, and displacement is simply the distance between where the starting point is and the ending point is. So again, distance is this total length of travel. Displacement is kind of, as the crow flies, this straight line from one point to the next point. Number 2, what's the difference between average and instantaneous speed? Speed, we know by its definition, is calculated by taking the distance you've traveled divided by the time. Average speed is found by dividing the total distance traveled by the total time taken. If you've ever taken a road trip, you got to think about the number of times that you've had to slow down, speed up, maybe you got caught in traffic, or you've got to change direction, you got to turn. There's all sorts of ways in which you're speeding up and slowing down, but the total average speed would be the total distance divided by the total amount of time taken. Instantaneous speed is a lot more precise in terms of it's taking right now at one instant of time. It's still using the same type of mathematical calculation as in distance divided by time, but it's taking at that specific instant. For example, if you're going down the highway, what's your speed at that top speed versus what's your speed when you're stopped at a stop sign? That's an instantaneous speed. Number 3, true or false? If you speed up, your velocity slows down. False. Speed and velocity are directly related to each other. In fact, you could say that they're the same in a way in which velocity includes the direction in which that speed is taking place. Number 4, true or false? If you slow down, your velocity slows down. That is true. If your speed is slowing down, your velocity is slowing down as well. Number 5, how is velocity and speed different? Well, velocity of an object is the speed of the object in the direction of its motion. So velocity also factors into the direction that object is traveling. A lot of times it gives us that direction by giving us west, south, north, east, northwest, southeast, the direction of travel as well. Number 6, what is the speed formula? Speed equals distance divided by time, or S equals D over T. Now in today's lesson, our objectives are to define acceleration and predict what effect acceleration will have on motion. We find ourselves on page 288. Let's begin. Acceleration and motion. When you watch the first few seconds of a liftoff, a rocket barely seems to move. With each passing second, however, you can see it move faster until it reaches an enormous speed. How could you describe the change in a rocket's motion? When an object's changed its motion, it's accelerating. Acceleration is the change in velocity divided by the time it takes for the change to occur. Like velocity, acceleration has a direction. If an object speeds up, the acceleration is in the direction that the object is moving. If an object slows down, the acceleration is opposite to the direction that the object is moving. What if the direction of the acceleration is at an angle to the direction of motion? Then the direction of motion will turn toward the direction of acceleration. Acceleration has direction. If an object speeds up, the acceleration is in the direction that the object is moving. If an object slows down, the acceleration is in the opposite direction that the object is moving. Speeding up. You get on a bicycle and you begin to pedal. The bicycle moves slowly at first, but speeds up as you keep pedaling. Recall that velocity of an object is the speed of an object and its direction of motion. Acceleration occurs when the velocity of an object changes. Because the bike's speed is increasing, the velocity of the bike is changing. As a result, the bike is accelerating. For example, the toy car in figure 7 is accelerating because it's speeding up. The speeding of a car is from 10 centimeters per second after 1 second, 20 centimeters per second after 2 seconds, and 30 centimeters per second after 3 seconds. Here, the direction of the car's acceleration is in the same direction as the car's velocity, to the right. So it's getting faster and faster and faster and slowing down. Now suppose you are biking at a speed of 4 meters per second and you apply the brakes. This causes you to slow down. When you slow down, your velocity changes because your speed has decreased. This means that acceleration occurs when an object slows down as well as when it speeds up. The car in figure 8 is slowing down. During each time interval, the car travels a smaller distance, so its speed is decreasing. In both of these examples, speed is changing, so acceleration is occurring. Remember that. If speed is changing, acceleration is occurring. If you're speeding up or slowing down, acceleration is occurring. Because speed is decreasing in the second example, the direction of the acceleration is opposite to the direction of the motion. Anytime an object slows down, its acceleration is the direct opposite of the direction of its motion. Changing direction. The velocity of an object also changes if the direction of motion changes. The object doesn't move in a straight line, but instead moves in a curved path. The object is accelerating because its velocity is changing, and in this case, the direction of acceleration is an angle to the direction of motion. Again, imagine yourself riding a bicycle. When you turn the handlebars, the bike turns. Because the direction of the bike's motion has changed, the bike has accelerated. The acceleration is in the direction that the bicycle turned. Figure 9 shows another example of an object that is accelerating. The ball that you're throwing up in the air starts moving upward, but its direction of motion changes as its path turns downward. Here the acceleration is downward. The longer the ball accelerates, the more its path turns downward towards the direction of acceleration. Our reading check. What are the 3 ways to accelerate? Here's 3 visual indicators. You can speed up, you can slow down, or you can change direction. You can turn. Anything that's turning or not traveling in a straight line is accelerating because it's in the form of a change of direction. Speeding up, slowing down, and changing direction are the 3 ways to accelerate. To calculate acceleration, we've got an equation that we're going to need to master and then do some mathematical calculations with. If an object is moving in only one direction, its acceleration can be calculated using this equation. Acceleration equation is the final speed subtracted from the initial speed divided by the amount of time that change takes place. Remember, because acceleration is when something is speeding up or when something is slowing down, you're going to take the initial speed and the final speed, or the 2 instantaneous speeds, and then find the difference between those by subtracting. However long that change took is how that acceleration is being measured in terms of meters per second, how fast something is speeding up or how slow something is slowing down. In this equation, time is the length of time over which the motion changes. In SI units, acceleration has units of meters per second squared. I'm looking at the example page on applying math on 290. It says to calculate the acceleration of a bus whose speed changes from 6 meters per second to 12 meters per second over a period of 3 seconds. Well, the initial speed is 6 meters per second, the final speed is 12 meters per second, and the time that this takes place is over 3 seconds. So you take the final speed, subtract from the initial speed, which would be 12 minus 6, which equals 6, and then multiply that or divide that by 3 to get a total answer of 2 meters per second squared. So it is speeding up at 2 meters per second. Every second it's going 2 meters per second faster. Okay? 2 other examples that are listed here on the page. Number 1 said the final speed is 0 meters per second and the initial speed is 12 meters per second. It took 3 seconds. Here's an example of your final speed being 0 and your initial speed being a calculated motion or speed. This means that you're slowing down. If the final speed is 0, you've come to a stop, like you're coming to a stop sign or a stoplight. So your initial speed was 12 meters per second, your final speed was 0, you would subtract that and you'd actually get a negative answer. 0 minus 12 is negative 12. Negative 12 divided by 3, because you take that change divided by time, would be a negative 4 meters per second. You're going 4 meters less every second because you're slowing down at that rate. Number 2, the final speed is 25 meters per second. The initial speed is 15 meters per second, and it took 5 seconds. Imagine that you're driving and then you need to go into a faster area, so the speed limit increases and you're going to increase your speed. Well, how did that acceleration take place? You increase by 10 meters per second over 5 seconds. That means you're going to take 25 minus 15 gives you 10 meters per second divided by 5. 10 divided by 5 is 2 meters per second to give you that overall acceleration. You're going 2 meters faster each second to get up to that final speed of 25 meters per second. Okay? Again, our equation looks like this. Final speed minus initial speed over time. If you ever have a negative acceleration, that means you're slowing down. If you have a positive acceleration, it means you're speeding up. Brings us to the next page, on page 291, positive and negative acceleration. As we read through this, I want you to think about examples of ways in which things have a positive or negative acceleration. An object is accelerating when it speeds up, and the acceleration is the same direction as the motion. An object also is accelerating when it slows down, but the acceleration is in the direction opposite to the motion, such as the bicycle in figure 10. How else is acceleration different when an object is speeding up and slowing down. Suppose you're riding your bicycle in a straight line and increase your speed from 4 meters per second to 6 meters per second in 5 seconds. You could calculate your acceleration from the equation on the previous page. 6 minus 4, your initial speed and your final speed. Subtract those, be 2 meters per second divided by 5. Your overall positive 0.4 meters per second comes from 2 divided by 5. That means you are speeding up, but it's kind of taking you a long time to get from one rate of travel to another. When you speed up, your final speed always will be greater than your initial speed, so subtracting your initial speed from your final speed gives you a positive number. Remember that. A positive acceleration means that you're speeding up. As a result, your acceleration is positive when you are speeding up. Suppose you slow down from a speed of 4 meters per second to 2 meters per second in 5 seconds. Now the final speed is less than the initial speed. You can calculate your acceleration as follows. 2 minus 4 is negative 2 divided by 5, which is giving you 2 divided by 5, which is negative 0.4 meters per second. If your initial speed and your final speed give you that negative value, you know that you are slowing down. Because your final speed is less than your initial speed, your acceleration is negative when you slow down. An example of speeding up or positive acceleration would be going from walking to sprinting, or from being at a complete stop to sprinting. Example of slowing down is when you're sprinting and you're maybe inside, like in a basketball gym. You've got to slow down, otherwise you're going to run into the wall. I got a story for you from a person I went to high school with. We were racing in the gym, and a group of students were racing from one baseline to the other baseline, going as fast as they possibly could. So they had to accelerate to speed up to full acceleration, and then they had to accelerate downward after they crossed that finish line. Well, this person wanted to win so bad that they weren't willing to de-accelerate or slow down in time, so they crossed the finish line and they were going to put their hands up to brace themselves on the wall, and when they did so, they hit so hard that they actually broke their wrists crashing into the wall. So acceleration can be positive and can be negative. It might be important to have that negative acceleration be cemented in your mind as something that you are slowing down, so you don't end up like that person who crashes into the wall. On the next page, graphing acceleration. The motion of an object that is moving in a single direction can be shown with a graph. For this type of graph, speed is plotted on the vertical axis and time on the horizontal axis. Take a look at figure 11. On section A of the graph, the speed increases from 0 meters per second to 10 meters per second. So that's right here, 0 to 10 meters per second for the first 2 seconds. So the acceleration is 5 meters per second because you're going to divide those two. The line in section A slopes upward to the right. An object that is speeding up will have a line on a speed time graph that slopes upward. So it's speeding up if it is going in this upward direction. Now look at section C. Between 4 seconds and 6 seconds, the object slows down from 10 meters per second to 4 meters per second, right here. The acceleration is negative 3 meters per second. On the speed and time graph, the line in section C is sloping downward to the right. An object that is sloping down will have a line on the speed time graph that slopes downward. So if you're slowing down, it's going down. If you're speeding up, it's going up. That makes sense. On section B, where the line is horizontal, the change in speed is 0. So a horizontal line on a speed time graph represents acceleration of 0, or a constant speed. Now notice that this is different from what we learned yesterday in our motion graph, because this is a speed versus time graph that's calculating acceleration. You've got speed versus time in terms of distance versus time. Because you still have a speed, this means that your speed is constant. Doesn't mean that you're not moving. On a distance and time graph, if it's like this, it means that you're not moving. On a speed and time graph, it means that you're at a constant speed. So maybe here's an example. You're getting onto the highway. You get onto the highway, you click into cruise control. You're going cruising, and now you're going to slow down. Obviously, if this is the course of 6 seconds. Maybe that's not a good representation, but shows speeding up, constant speed, slowing down. Okay? That should help you with your homework, as your homework looks like this. In numbers 1, 2, and 3, it says, in the space provided, substitute a word for the word in italics to make the statement correct. So the words that are in italics here are ones that need to be corrected. Put those correct terms in the blanks right here. In numbers 4, 5, and 6, answer the following questions on the lines provided. In numbers 7, 8, and 9, it says, study the velocity time graph for an object in motion, then answer the following questions. Let's go ahead and do this one together. Number 7, in what interval does the object have the fastest acceleration? Well, we just learned that when an object has this upward direction, that means it's accelerating. The object speeding up has an upward slope, and you probably already recognize that if it's steeper, that means it's speeding up faster. If it's kind of not as steep, it's speeding up at a slower rate. So the steepest area means that that's where it's speeding up the fastest. That should help us answer number 7. In what interval does the object have the fastest acceleration? It's going upwards here, so it's got positive acceleration. It's going upwards here, so it's got positive acceleration. It's going upward here, so it's got positive acceleration. Notice the question doesn't say where it has positive acceleration, where's the fastest acceleration. So what's the steepest overall? It looks like positive acceleration from letters D to E is the fastest, but in terms of overall acceleration from G to H would be accepted as well, because this looks like the steepest line overall. It means like you're coming to a sudden stop because it's going downwards, but it's still considered acceleration. Number 8, over what interval or intervals does the object have a negative acceleration? That's anywhere in which the line are going downward. So here's the example from C to D. You would just write CD right next to each other and then put a line right over the top for your line segment. And then from G to H, another answer for this one, because it's a negative acceleration, it's going downwards in that example as well. Number 9, over what interval is the object stopped? Can't say that the object is stopped from B to C, because this means that it's speeding up, going at a constant speed, slowing down, speeding up, speeding up, speeding up, and then slowing way down all the way to a stop. Looks like here, because the velocity is at 0, that means you're not moving from H until I, you would be overall stop. So here it's HI for number 9. Hope that helps. God's blessings.